Hello. In this section, we are going to explain the concept of time series data. We're going to discover how it differs from other types of data you've previously encountered and why time series analysis is tricky. After that, we'll introduce you to some of the most basic time series notation and terminology. Let's begin with the definition. Time series is a sequence of information which attaches a time period to each value. The value can be pretty much anything measurable that depends on time in some way, like prices, humidity, or number of people. As long as the values we record are unambiguous, any medium could be measured with time series. There aren't any limitations regarding the total time span of our time series. It could be a minute, a day, a month, or even a century. All we need is a starting and an ending point. Usually, there are many other points in between the start and the end of a time series. The interval of time between recording one point of the set and the next is called a time period. How often values of the dataset are recorded is referred to as the frequency of the dataset. To be able to analyze time series in a meaningful way, all time periods must be equal and clearly defined, which would result in a constant frequency. This frequency is a measurement of time and could range from a few milliseconds to several decades. However, the ones we most commonly observe are daily, monthly, quarterly, and yearly. Furthermore, patterns observed in time series are expected to persist in the future. That is why we often try to predict the future by analyzing recorded values. Okay, great. Now that we've learned the main features of time series data, namely every value is associated to a time period, intervals between said periods are constant, and patterns persist into the future, let's look at some examples. Meteorologists often cope with the task of forecasting the weather for days ahead. To make even remotely accurate predictions on a consistent basis, they rely on analyzing past data. Needless to say, if the data is not ordered chronologically, finding the correct pattern would be extremely difficult. For instance, simply knowing the highest temperature for the last 5 days would be useless unless we know which value corresponds to each day. Why? Because chances that the temperature rose 5 days in a row or dropped 5 days in a row are equal. Thus, without the corresponding time periods for each value, the data is much less relevant. All right, let's talk about business. In the world of business, time series data is largely applied in finance. For investors, as well as company owners, it's crucial to determine whether prices, returns, profits, and sales will increase or decrease in the future. Therefore, a common topic in time series analysis is determining the stability of financial markets and the efficiency of portfolios. Now, time series data is usually time-dependent. This means the values for every period are not only affected by outside factors, but also by the values of past periods. For instance, we expect tomorrow's temperature outside to be within some reasonable proximity to today's values. Furthermore, time series data can suffer from seasonality. Some values like rain or temperature vary depending on the time of day and the season of the year. Since it's a repeating cycle, we can anticipate these changes and account for them when making our predictions. Seasonality as a trait isn't often observed in regular data, and that is only logical. When there is no chronological order, we don't expect repeating cycles, right? Great job so far. To express time series efficiently, we need to introduce some notation. Thanks for watching. Hello. In this short lecture, we're going to introduce the most prevalent notation used in time series. Let's begin. We describe time series variables with capital letters of the Latin alphabet, like X or Y. For example, we can label the prices of the S&P 500 over some period of time as X. We describe the entire period covered by a time series with capital T, while we use lowercase t to describe a single period within the interval. Now, imagine we had the daily closing prices for the S&P 500 for the entire 2008. Given the uppercase T represents the entire year, the lowercase t would represent a single day. Then, to denote the closing price at a specific day, we would use X of T. Alternatively, we could simply write the precise date, time, or year as a subscript. Since t represents the order of the period we are interested in, we express the previous period as t minus 1. Similarly, we can express the next period as t plus 1. This notation will be extremely helpful when we try to model time series data to make predictions about the future. Fantastic! Now that you're familiar with the basics of time series, we can discuss some peculiarities of its data. Thanks for watching. Hello there and welcome back. This lecture revolves around a few specifics you should be aware of when analyzing time series data. Keep in mind that some concepts may be a bit fuzzy. Even so, this lecture will still serve as a roadmap, and you will see that it will help us overcome the hurdles we will experience throughout this journey. For starters, as we already mentioned, the intervals between different observations need to be identical. If this is not the case, it's usually due to some missing values. In time series, dealing with missing values is much more complex compared to other types of data. This can be explained by the fact that values between consecutive periods usually affect each other. And this can stir tons of trouble. So we must find ways to handle such limitations. Let's take a look at another oddity of time series data. Namely, we can adjust the frequency of a dataset depending on the values we are interested in. For example, if we have daily data but want to conduct a monthly analysis, we need to compute some average value of all the individual daily values. In this case, by aggregating the data, we will try to determine the best way to describe each month. Sometimes we have to increase the frequency. This leads to an increase in the number of time periods within the interval, and consequently, to new time periods without any values assigned to them. To analyze the data successfully, we need to approximate or impute values for these periods. And there's more. Unlike regular data, time series data requires chronological order. From a machine learning perspective, this is inconvenient because we cannot freely shuffle the data before separating it into a training and a testing dataset. What we must do instead is pick a cutoff point. The period before the cutoff point is the training set. The period after the cutoff point is the testing set. There's yet another difference for time series data. Its graphs do not follow any of the standard distributions you may be familiar with from statistics and probability. Strange, right? Well, it's because time series data never satisfies Gauss-Markov assumptions, unlike regular linear regression data. Instead, time series data assumes that past patterns in the variable will continue unchanged into the future. Using this approach, we will forecast our predictions about future values. Great job! So besides time series modeling, you can expect all types of pre-processing while we're trying to deal with the issues mentioned. But before we dive into those, let's get our hands dirty with some Python coding. Thanks for watching. Hello everybody. After getting familiar with time series, it's time to get started with some coding. Before we move on, we advise you to download the index2018.csv file accompanying this lecture. To begin with, load up Jupyter and import all the relevant packages for this section. In this lecture, we will only require the NumPy and Pandas packages. We won't need the rest of these packages, so we can comment them out before running the cell. Now, to import the data from the CSV file, we will create a data frame object using the Pandas module. We name the variable raw_CSV_data and use it to record the values from the integrated function read_CSV from the Pandas package. Inside the parentheses, in double quotation marks, we add the name of the file we downloaded earlier, index2018. Make sure you save the file in the same directory as your Python code. Otherwise, you have to specify the exact folder where you stored it. If you happen to do so, make sure to use // when setting the appropriate directory. Remember, backward slashes serve a different purpose in Python. Right. Before we start manipulating the data, we must create a copy of our original data. So even if we happen to erase certain values from our dataset, we can always refer back to them without reading the CSV file again. To create this additional data frame, we simply set the new variable equal to raw_CSV_data.copy parenthesis. In this case, I've decided to name the new variable df_comp to indicate this is the complete data frame. Time's precious, so let's start examining the data we loaded into Python. In the next lecture, we will explore the dataset and try to draw insights based on the summarized statistics. See you in the next lecture. Welcome back. In the previous lecture, we imported data from the CSV file into a data frame object. In this one, we will take a closer look at the dataset and the values it contains. For starters, use the .head method to examine the top 5 observations for the dataset. We can also write df_comp, which will showcase the entire dataset. This gives us a great idea of what the full data looks like, but it can slow down the computing process for really big datasets. The first column is called date, and it represents the day when the values of the other columns were recorded. We usually analyze time series in consecutive chunks of data, from one date to another. For instance, many scientific papers on the Great Recession use 15th September 2008, the collapse of Lehman Brothers, as a starting or ending point. Therefore, we usually use dates as indexes for time series data. The next 4 columns represent time series data for the closing prices of 4 market indexes: S&P 500, DAX 30, FTSE 100, and Nikkei 225. Each market index is a portfolio of the most traded public companies on the respective stock exchange markets. To be more precise, the S&P, DAX, FTSE, and Nikkei measure the stability of the U.S. stock exchange, the German stock exchange, the London stock exchange, and the Japanese stock exchanges, respectively. Also, the numbers following each index represent the number of companies included in the portfolio. So, the German DAX consists of only 30 companies, while the U.S. S&P contains 500. Great. To understand the data frame in more detail, we can use the describe method. Simply type in the name of the data frame. In our case, it is df_comp, and add .describe. Recall that method requires using parentheses at the end, so make sure you add those before running the cell. Notice that we only get summarized information about the 4 market indexes. That's because date is non-numeric, and the default setting of the describe method omits such variables. The first line of this table is called count. It shows how many observations are recorded for each column. In our case, we have 6,269 values for each series. We only recorded dates when we had available data for all 4 indexes, so having an equal number of values is to be expected. The second line shows the average values for all the elements of each series. Notice that the average price for the S&P is several times lower compared to other indexes. Furthermore, the maximum value for the S&P is lower than the minimum value of FTSE and Nikkei. Therefore, we take into account this huge difference in magnitude when comparing multiple time series. For the moment, it suffices to say that the values for the DAX and FTSE are similar, while the S&P and the Nikkei are a lot smaller and larger, respectively. Earlier, we mentioned that time series often have missing values. Lucky for us, data frames have a built-in function for determining not available or NA elements, called isNA. The function returns true if the element is NA and false if it isn't. If we write df_comp.isNA, Python will print out a table which includes true or false values for all 4 market indexes in any time period. To establish the number of missing values, we have to explore the entire table. Alternatively, we can take advantage of some ready-made methods from pandas. Most programming languages, including Python, use 1 as the equivalent of true and 0 as the equivalent for false. Thus, by finding the sum of all the corresponding values for every element of a time series, we should get the number of missing elements. If we type in df_comp.isNA parenthesis .sum parenthesis and run the associated cell, we can get the number of available entries for each column. Alternatively, we can specify which object we are interested in by referring to it instead of referring to the entire data frame. For instance, if we are only interested in the S&P values, we should add .spx after the name of the data frame and rerun the cell. This is convenient when we are dealing with a huge database, especially when there are too many individual columns we are not interested in. Great job so far! Looking at summarized statistics gives us a general idea of how spread out each series is. However, it does not provide us with a sense of how the values evolve with each period. A common practice in time series analysis is plotting datasets to see how the data develops over time. Head to the next lecture to see how it's done. Thanks for watching. Welcome back. It's time to plot the time series data. Okay, since the dataset contains 4 different time series, we can plot each one on their own to see how they change over time. Let's begin with the S&P 500. Recall that the formal abbreviation of the market index is SPX. Quite convenient. That matches the name of the data frame column containing the values. Right. To call the plot method we mentioned earlier, we need to refer to the appropriate object in the data frame. Let's write the name of the data frame followed by .spx.plot. Since it is a method, Python syntax requires us to add parentheses at the end. Depending on your version of matplotlib, you may also need to call the show method. So, on the line below, I'll write plt.show followed by parentheses. Let's run the cell and observe the graph. Recall we can use the shortcut Ctrl+Enter to run this single cell. Notice that the x-axis consists of numbers. These numbers represent the periods the values come from. If we are dealing with proper time series data, the x-axis will show the corresponding dates for each period. For instance, period 0 will express the first date of the dataset, which is January 7th, 1994. This occurs because the indexes for each period are simply numeric values, rather than dates. In a couple of lectures, we will show you how to amend this problem. But for now, let's focus on the plots. Since we are going to explore how time series fluctuate, we should find a convenient method to keep track of which plot represents which series. The easiest way to accomplish this is by naming the graphs. We do so by giving a value to the title argument of the plot method. Since we map the S&P 500, we can add title equals S&P 500 prices. Make sure you put the name in quotation marks to avoid getting error messages. By running the cell again, we get the same graph as before, but with a title at the top. Additionally, we could stretch the graph so we can observe how values change more closely. To do so, we set the fig size parameter value equal to 20, 5 in parentheses. Great work! Observe how the price of the S&P fluctuates. There are periods of booming growth, followed by sharp falls. The first 2 large peaks, followed by periods of turbulence, represent, of course, the .com and the housing market bubble, respectively. We should also plot the graphs for the other market indexes to see if they followed similar patterns during these periods. For instance, let's see how FTSE values changed over time. We can copy the code we used for the S&P, but change the attribute of the data frame from SPX to FTSE. We should also change the title parameter to accurately reflect what this graph represents. The new plot we observed shows similar patterns for the 2 bubbles we mentioned earlier. That can be explained by the parallel of the US and the UK stock exchange markets. Of course, when analyzing several data series, we want to compare them. To do so, we can put the graph of the S&P and FTSE on the same plot. We can achieve this by plotting both series in the same cell. Before we run the cell, we should call the title method from the matplot and name the graph. Otherwise, the new graph would take whatever name we defined last. Observe how FTSE values are much greater than the S&P ones, but the 2 still move similarly. One major difference is that the S&P looks much flatter than the FTSE, which would suggest the S&P is much more stable. However, this is misleading. The graph of the S&P looks more compact because of the magnitude with which values for the S&P and FTSE change. This is one of the reasons time series analysis involves compounded returns along with prices, but more on that later. Fantastic. So far we only plotted prices against time, but what if we want to know the density of the data and which values are more likely to occur? To do so, we should construct the quartile-quartile, or the QQ plot. But more on that in the next lecture. Thanks for watching. Welcome back. In this lecture, we are going to introduce what a QQ plot is and how to interpret it for a series of values. Let's begin. The quantile-quantile plot, or QQ plot for short, is a tool used in analytics to determine whether a dataset is distributed a certain way. Unless specified otherwise, the QQ plot showcases how the data fits a normal distribution. Before we get into details about what the QQ plot represents, let's see how it looks. For starters, call the prob plot function from the SciPy stats package. To do so, type out scipy.stats.probplot. In the parenthesis, define the two key parameters for this function. The first one is the series we want to test, and the second one is the way we want to express the plot. Suppose we are interested in the S&P. Then we would add df_comp.spx as the first parameter. Then we need to specify what type of plot we want to use. Usually we add plot equals pylab. Before we run this cell, we need to print out the plot, so we call the show function for pylab. All right. Let's examine the QQ plot and what it represents. For starters, the QQ plot takes all the values a variable can take and arranges them in order. The y-axis expresses the price, with the highest ones at the top and the lowest at the bottom. The x-axis represents the theoretical quantiles of the dataset. Another explanation for the latter is how many standard deviations away from the mean these values are. The red diagonal line on the screen represents what the data points should follow if they are normally distributed. In this case, we see that it is not really the case, since we have more values around the 500 mark than we should. Therefore, the data is not normally distributed, and we cannot use the elegant statistics of normal distributions to make successful forecasts. However, this is what we usually expect from time series data. Now that we are familiar with the dataset, we can move forward and start some in-depth analysis. In the next section of the course, we will convert our data frame into a time series. We will set the frequency of the data and account for any issues that may arise from that. Additionally, we will split up the data into a training and testing set so that we can use machine learning to make forecasts about the future. Our journey is just getting started. Thanks for watching.